Welcome to the Deep Dive. We sift through the latest research, the data, the articles, so you get the full picture.
Today we're looking at 3IATLAS. It's only the third object we've ever confirmed coming from another star system.
And our goal here is to really unpack what makes this one so different. Because it looks like a comet, sort of, but it's chemistry. It's got scientists seriously rethinking things.
Yeah, it's forcing what some are calling a paradigm shift about these interstellar visitors. The data, especially from JWST, is just, well, it's pretty stunning.
So let's lay out the basics first. It was discovered mid-2025 by the ATLA survey, hence the name. 3I means third interstellar object.
Right. And the key thing is its path. It's got this highly hyperbolic orbit, eccentricity about 6.1, which basically means it's absolutely not bound to our sun.
It's just passing through. And fast, right? Something like 130,000 miles per hour?
Over 60 kilometers per second, yeah. Gone. Which puts it in the same category as our first two visitors, but they were so different from each other.
Exactly. You had one Oumuamua, which was weirdly rocky, kind of cigar-shaped, and accelerated without obviously venting gas.
Still a puzzle, that one.
And then 2I Borisov, which was, well, much more like a standard comet icy with a clear tail.
Looked pretty familiar, yeah. But 3I-8less.
Yeah.
It's the confusing middle ground.
That's the hook, isn't it?
Yeah.
It acts like a comet, big cloud of gas, shedding material, but when we actually looked closely at what it's shedding, it just doesn't match almost anything in our own solar system.
Precisely. It's a genuine alien artifact in the sense that it came from elsewhere, but its properties are forcing us to question our assumptions.
Let's maybe start with the physical weirdness.
Okay, yeah. What were the first red flags for astronomers as it came closer?
Well, first off, its size. The estimates were, frankly, all over the place initially, but they pointed to something potentially huge.
How huge are we talking?
Estimates range from maybe 440 meters, which is respectable, up to possibly 5.6 kilometers across.
Wow, that's significantly larger than Oumuamua or Borisov. Potentially, yeah. And then there's when it started acting like a comet.
It lit up really early, didn't it?
Way earlier than expected. We saw signs of activity like shedding ice and gas when it was still way out at 6 AU.
6 astronomical units. That's Jupiter distance, roughly.
Exactly. Most comets from our own Oort cloud don't really switch on until they get much, much closer to the sun, maybe inside Mars orbit.
So it's hyperactive even out in the cold depths of space.
Very volatile, yeah. And then there was that strange anti-tail feature people saw early on.
Right. I remember seeing images. It looked like it had a plume pointing towards the sun. That seems wrong.
It does seem counterintuitive, but it's thought to be real, not just an optical trick. It suggests really intense outgassing happening preferentially on the side facing the sun, even far away, like super volatile stuff boiling off very easily.
Okay, so physically it's big, surprisingly active far from the sun, and has this weird sunward plume. But the real shock came from the chemistry, starting with the VLT observations.
That's where it got really perplexing. The Very Large Telescope detected atomic nickel vapor in its coma, the gas cloud around it.
Nickel, why is that weird?
Because at those temperatures, metals like nickel and iron should be locked up tight inside rocky dust grains. They shouldn't be floating around as individual atoms in a gas.
So something was blasting these grains apart, or the nickel wasn't locked up properly?
Something like that. But the real kicker was the ratio.
Ah, yes.
Yeah.
The nickel to iron thing.
Exactly. They saw a strong signal for nickel, but comparatively very little iron.
Which is strange because...
Because in nature, especially in meteorites and cosmic dust, iron and nickel tend to occur together in fairly predictable ratios. Finding lots of nickel gas without much iron gas is, well, it's very odd. It almost looks like some kind of processed alloy, not natural rock.
Okay, that VLT finding alone is bizarre. But then the James Webb Space Telescope turned its eye on it. This is where things get really wild, right?
This is the revolutionary data. JWST used its infrared spectrograph, NIR-SPEC, to analyze the composition of the coma in detail, and the result was just unambiguous.
What did it find?
Carbon dioxide. Overwhelmingly, the coma was absolutely dominated by CO2 gas.
Wait, not water. I thought water ice turning to gas was the main engine driving comets.
It usually is, especially closer in. But out where ATLAS was observed, around 3 to 4 AU at that point, the coma was found to be surprisingly water poor.
Okay.
The measurement they got for the CO2 to H2O mixing ratio was $7.06 p.m. as says in 3/3 pounds.
Right, $7.66. How unusual is that number in context?
It's off the charts, completely unprecedented. That ratio is something like 18 times higher than we'd expect for a typical solar system comet observed at that same distance.
18 times. Wow.
Statistically, Basically, it's what we call a $4.05 sigma outlier.
And for people not into statistics, $4.05 sigma basically means?
It basically means there's an incredibly tiny chance, like less than 1 in a million, that this object belongs to the same family as the comets we know. It's fundamentally different. Its gas composition is alien.
So not much water, tons of CO2. Did they see anything else?
Yeah, they also saw quite a bit of carbon monoxide, CO, as well. The CO to water ratio was also high, about $1.655. But the sheer dominance of CO2 was the headline result.
Okay, so we've got this picture. Huge object, hyperactive way out, weird nickel signal, and it's breathing almost pure CO2 instead of water vapor. This thing clearly isn't like our local comet. So how did it get this way? If it didn't form like this, what happened to it?
And that question leads us directly to the most compelling explanation currently on the table, the one that seems to tie all these anomalies together. Galactic cosmic ray processing, GCRs.
Right, the idea that its long journey through the galaxy changed it. Not its origin, but the travel itself.
Exactly. You have to think about the timescales involved. Based on its trajectory and speed, dynamical models suggest 3IATLAS could be incredibly old. Maybe 3 billion, maybe even up to 11 billion years old.
Older than our solar system, potentially.
Potentially, yes. And for all that immense time, billions of years drifting through interstellar space, it's been constantly bombarded.
By what?
By galactic cosmic rays. These are high-energy particles, mostly protons, some heavier atomic nuclei accelerated by supernovae and other energetic events across the galaxy. They zip around everywhere.
So this comet was basically getting zapped by radiation for billions of years?
Continuously. And lab experiments, combined with modeling, show what this does to ices. These GCRs are very effective at driving chemical reactions.
What kind of reactions?
Specifically, they can convert simpler primordial ices like carbon monoxide, CO, into more complex and stable molecules like carbon dioxide, CO2.
Ah, so the GCRs could literally create all that excess CO2 that JWST saw.
That's the idea. Over billions of years, the GCR bombardment penetrates the outer layers of the nucleus and transforms the original CO ice into CO2 ice. This neatly explains that extreme CO2 dominance.
Does it do anything else? Does it change the physical structure?
Yes, absolutely. This radiation processing doesn't just change the chemistry, it fundamentally alters the surface layers. It creates a sort of crust.
A crust, like baked hard.
Sort of. It becomes chemically altered, often reddish in color due to complex organic molecules forming. It's enriched in these processed ices like CO2, and it likely becomes more compacted.
And that crust could explain why it was so active so far out.
Potentially, yes. Maybe the sun's heat had to penetrate this altered layer, and when it did, it hit this highly concentrated CO2 reservoir, causing that vigorous early activity.
Okay, now here's the part you call the paradigm shift. What does the existence of this GCR processed crust mean for what we're actually seeing?
This is the crucial point. The models suggest this altered crust isn't just a thin veneer. It could be quite deep, maybe 15 to 20 meters deep.
15 to 20 meters, that's pretty thick.
It is, and here's the punchline. Calculations show that even with its early activity, the amount of material 3IATLAS actually lost through sublimation as it flew towards the sun before its closest approach was probably less than 1 meter.
Wait, so the process layer is 15, 20 meters deep and it only lost less than a meter?
Exactly. It means that all the gas we observed, all that record-breaking CO2 measured by JWST, all the weird nickel, it was all coming from this altered, processed, GCR-irradiated crust.
So we weren't actually sampling the original pristine material from its home star system at all.
Not yet. We've been sampling the weathered surface, the result of its multi-billion-year journey through the galaxy. And this is the paradigm shift. Interstellar objects aren't necessarily pristine messengers carrying untouched samples of their birthplaces.
They're process messengers. They carry the story of their journey written onto their surfaces.
Precisely. They are survivors, shaped by the interstellar environment itself.
That is a huge realization. It reframes how we have to interpret data from Oumuamua and Borisov, too, potentially.
Yeah.
But, you know, whenever you have anomalies this strange, the alien idea comes up.
Inevitably, yes. And it's important to address it, particularly since some prominent researchers like Avi Loeb at Harvard have specifically argued that we shouldn't dismiss an artificial origin out of hand for objects like this.
What are the main arguments from those who lean towards, or at least want to consider, an artificial explanation for 3IATLAS?
Well, they point to a few things. One is the trajectory itself. Coming in at only 5 degrees to the ecliptic plane, the flat plane our planets orbit in, is seen by some as statistically unlikely for a random visitor.
Like it was aiming for the busy part of the solar system.
Sort of. Combined with the convenient flybys of Mars and then Jupiter, some frame it as looking almost like a planned reconnaissance path, however unlikely that sounds.
Okay, what else?
The size and mass. LOBA estimated its mass could be over 33 billion tons. The argument is, if natural objects follow a typical size distribution where small things are common and huge things are rare, why haven't we seen thousands of smaller interstellar objects before spotting this giant? It seems statistically backward.
The size paradox and the chemistry.
Yes, the weird nickel-to-iron ratio gets mentioned again, suggesting maybe it hints at industrial alloys. And the extreme CO2 dominance is so unusual it gets flagged as potentially non-natural.
But how does the broader scientific community, NASA, ESA, the teams actually running the telescopes, respond to these points?
The overwhelming consensus remains that it's a natural object behaving in very interesting but ultimately physically explainable ways. The line you hear is essentially, it looks like a comet, it acts like a comet, albeit a very weird one.
So the GCR model is seen as robust enough to explain the anomalies.
Yes. The GCR processing model, which is based on known physics and lab data, actually provides a coherent explanation for the CO2 excess, the early activity, and even potentially the nickel signature GCR impacts might preferentially liberate nickel atoms from certain mineral structures compared to iron.
It's complex, but it fits the data without invoking new physics or technology.
Right. And there's always the caution against the alien of the gaps argument, essentially saying it must be aliens, just because we don't immediately understand every detail. Science often finds natural explanations for things that initially seem baffling.
The key seems to be that the GCR explanation is grounded in observable physics, even if it's complex.
Exactly. The data from 3IATLAS didn't invent GCR processing, but it provided such strong evidence for it that it forced the astronomical community to fully reckon with its effects on interstellar objects. It's now seen as a major factor we have to consider.
Okay, so the object made its closest pass to the Sun, perihelion, back in late October 2025. It's heading out now,
Yeah.
but the science isn't finished, right?
Not at all. There was a massive all-hands-on-deck effort to observe it, especially around perihelion when it was hardest to see from Earth because it was lost in the sun's glare.
So how did they track it then?
Using our eyes near other planets. ESA's spacecraft orbiting Mars Express and the Trace Gas Orbiter were able to observe it during its Mars flyby around October 3rd.
Clever. Using Mars as an observation post.
Exactly. And there's still hope that NASA's Juno spacecraft, which orbits Jupiter, might get a look as 3IATLAS swings by Jupiter around March 2026. It's a true interplanetary observation campaign.
And scientifically, what's the big question they hope to answer with these ongoing observations, especially now that it's past perihelion, given the GCR crust idea?
The ultimate test is to compare the composition before perihelion with the composition after. The hope is that the intense heating during its close pass to the sun might have finally eroded away more than just that top meter.
So maybe it blasted through the 15-20 meter processed crust.
That's the hope. If it eroded deeply enough, we might start seeing gas coming off that has a different chemical signature, perhaps less CO2, maybe more water ice, reflecting the deeper, more pristine, primordial material from its home system.
So if the chemistry changes significantly as it recedes,
That would be the smoking gun. Confirmation that we finally punched through the GCR weathering layer and are tasting the original ingredients from another star system. That comparison is absolutely key.
so wrapping up, 3IATLAS is really shaking things up. It's shown us these interstellar visitors aren't just static relics.
Not at all. They're dynamic objects, profoundly altered by their immense journeys through galactic space. They wear their travel history on their sleeves, chemically speaking.
It's a fundamental shift from thinking of them as pristine time capsules, seeing them as process survivors.
Absolutely. And it leaves us with a really provocative thought, doesn't it? If galactic cosmic rays could build up a 15 or 20 meter deep altered crust on 3IATLAS over billions of years, what does that imply about Oumuamua and Borisov?
They were likely just as older and smaller.
Exactly. They would have been subjected to the same processing. So the question becomes, have we ever actually sampled the truly pristine, unaltered interior material of any object from another star system, or have we only ever seen the weathered, processed exteriors? That's a huge question for future missions and observations.